Good afternoon, everyone. It's my great honor to introduce the eminent speaker, Dr. DIpankar Banerjee. He is currently the director of the ARIES Research Institute of Observational Science, Nainital. He is an astrophysicist with a bachelor degree in physics from St. Xavier's College and master degree in theoretical physics from University of Calcutta. He has obtained his PhD degree from Indian Institute of Astrophysics and completed 2 postdoctoral tenures in reputed institutions in Europe. He is also a senior professor at the Indian Institute of Astrophysics. Dr. Banerjee's area of interest is the Sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the Sun and its impact on space weather. He is the co-chair of the Science Working Group of the Aditya mission. Aditya is the first dedicated Indian mission to study the Sun, expected to be launched by ISRO around 2023. He is also involved with NASA's Punch mission. He is fellow of the Indian Academy of Science and National Science Academy and currently the president of the Astronomical Society of India. Dr. Banerjee has more than 150 peer-reviewed publications with around 100 citations in the international journals. He is currently supervising 5 PhD students, while 15 of his students have completed their PhDs. Apart from his scientific career, Dr. Banerjee has interest in various other activities. He is trained in Hindustani vocal and part of a Bengali theatre group, Swarannik, and regularly performs in plays participating in the national and international theatre festivals. Dr. Banerjee's love for science and zest for life are infectious. With this brief introduction, I would like to request Dr. DIpankar Banerjee to start his presentation. Thank you.
Thank you very much for your kind introduction. I think when you take it from the web, it slightly needs updated because the launch is tomorrow. So you have to excuse me. Just after this talk, I have to rush to the airport to reach Sriharikota in the night. First of all, it's a really nostalgic moment for standing here today. As you can imagine, in the 80s, I was there in this campus. And some of the names which I heard during the last presentation, they were all over, our forefathers and the teachers. Incidentally, Professor Jagadish Bhattacharya was the director when I joined as a PhD student. And I carried a MSc certificate with the name DIpankar Banerjee. And the administrative officer said, "This is not your certificate. You have been enrolled as DIpankar Banerjee. Please prove this." So I had to, of course, reach out to Professor Bhattacharya, and he certified that this is the same person, so please enroll him. So I think this auditorium also is very, very, nostalgic for me as well. We heard a few lectures when I was a master's student here. There used to be Saha Institute, used to come to the canteen to get the good quality food because our canteen was not as that good. So, in many ways, the names what we heard, Ananta Krishnan, he's been in our governing council and so on. It's really, really my great honor to be here. That's why I didn't want to refuse it after this launch date was scheduled. I rushed here yesterday night and I had to rush back to the airport. So please excuse me for that. So what I plan to do today is, again, the title was given a few weeks or months back before the launch date was given. So I was planning originally to talk about the variability of our nearest star, and of course Aditya mission is dedicated for that study, and I will try to give you importance about Aditya. So first of all, I can just stand here. Yeah, the people who are sitting in the back may not be able to read anything in the slides. So I would request people to come forward because the content, some of the text are there, although I will be reading out some but not all. So this is too much of a distance to read. I went there and I found I can't read myself. So please come forward if you want to really read out what is there. So I'm coming from this beautiful place at Nainital. This is my office, but currently we host the two largest 4-meter class telescope from Devastan. This is our observatory, this is nation's pride. But I work on the sun. Sun is our nearest star. It's a middle-aged star, but it is a special star because it gives us all the energy, and also it allows us to see the details because we are spatially able to resolve this structure. Most of the other objects are seen as a point object. Of course, it is here. Our existence is here because of the presence of the star at an appropriate distance away. But otherwise, as a student of physics, it really allows us to verify different branches of physics. Frankly speaking, when I went for my PhD interview in Institute of Science, I did not get a chance in the physics interview. That's a reality. I was selected in the astrophysics, but I didn't have any clue that what I'm going to do in my PhD. But sun, was an object which I could relate with my basic understanding of theoretical physics. Whether you call it atomic physics, molecular physics, nuclear physics, particle physics, almost any branches you can, use for getting unsolved problems in solar physics. So the variability what you see in the sun is of different time scales. There are short-term variabilities, there are long-term variabilities also. And the physics involved in this different variability, time scales and spatial scales are very different. Because when you talk about, long-term variations, you will know that the internal structure of the sun, which generates the magnetic field and so on, through the process called dynamo, is more responsible. Whereas when there are very dynamic, fast transient events happening in the atmosphere, of course it is again the magnetic field which is responsible, but the variability time scale or the instability time scales are very different. So the physics involved is very different. And then you go to larger distance away from the sun. In the heliophysics, of course, the scales are very different. The densities fall up to many orders of magnitude. So you cannot apply the same hydrodynamics or magnetohydrodynamic physics. You have to go into kinetic physics and so on. So the domains are very different. So before I get into the modern day, of course, we have to always remember the history, and we are nostalgic today when we are recalling how the science has evolved, and even the radio observation and the solar radio observations were so important in the context. This all started from Galileo more than 400 years, but then we now understand that the sunspots are magnetic structures that emerge from beneath the surface, like these flux tubes. As I said, they are believed to be generated in the base of the convection zone. This is the internal layers of the sun, and then through a dynamo process we explain their origin and evolution. But then when these tubes come out, and as you see in this movie, they get tangled, and then because of the instability, whatever material is confined within this, that they are expelled. So today actually I will be probably talking about more on that, but just please remember that this is also a very important area. What is plotted here is the sunspot number for last 400 years. So as you can very clearly see, there is an alternation of the sunspot number which represents the changes in the magnetic activity of the sun. And we have a typical 11-year periodicity. You are hearing about Arnold Raychudhuri's name, so he has spent on his life on this, explaining the origin of this and also why these cycles are so different. You see, one cycle has a much larger amplitude as compared to the other amplitude cycle. And there are serious impact of these variations in the cycle amplitude, cycle durations, and so on. So this is again another very, very important area which we need to understand, because the overall solar impact on our climate is crucially dependent on understanding the solar cycle. So that's again one area, and one of the payloads in Aditya also is going to dedicate its activity towards that. So some places, I've been saying that though it is a 5-year mission, Aditya, expect it to live for at least one solar cycle, but it does allow us to go back into the history and also talk about the future. So that's why the solar cycle, studies are also very important. So in the sun, we know that there are these strong magnetic regions called sunspots, but then when we see sunspots here on visible wavelength, we need to know what is happening in the atmosphere. So if you want to see the atmosphere, you have to go to other wavelengths. And this is true for any astronomy you do today. Modern day astronomy demands multi-wavelength, because multi-wavelength allows you to probe different plasma, and then only you get a comprehensive view about whatever is the source region. So here, I'm just showing you again example that these sunspot regions, they are connected by these kind of long loop kind of structures. This is taken in the coronal height, which is about 2000 kilometers. This is in the chromospheric height, which is about 1500 kilometers. You see these loop structures are more compact here, whereas these guys are much more extended. And then sometimes they live for several days to weeks, but then eventually they explode. So the point I'm going to again highlight today is it is so much important to have a multi-wavelength observational capability, which we didn't have from India, and that's why Aditya is going to change our life as far as solar physicists from this part of the globe. Again, this is a classical example to highlight. If you have seen only a telescope, which we have been doing for the last 700 years, sun would have looked a little boring, flat in white light. Of course, there are small little dots which you can see from a distance. They are called sunspot. But if I see it infrared, you see already those spot regions, look so different. And then if I go to, even shorter wavelength, namely the ultraviolet or X-rays, these are images taken from again space platform. You see so much of complexity in the sun. This is just a screenshot. Of course, we can take every few milliseconds now an image. So it is so dynamic that it is now possible to really see the evolution of these magnetic things. So this is a state-of-the-art kind of active region things we are able to see from NASA satellites. This is a satellite called Solar Dynamic Observatory. When this huge magnetic structure which becomes unstable, you see a lot of material is thrown into the interplanetary space, but then some material falls back as well. Now the question would be that when these huge material is thrown into interplanetary space, what would be its trajectory? First of all, we need to understand why this guy is, becoming unstable and creating this ejecta. Then it will be important to understand that if it is thrown into the interplanetary space, at what speed it can travel. So to do that, we need to sometimes look with the full disk images, but then we need to follow its trajectory into the outer space as well. So for that matter, we make collection of instruments. This is called the coronagraph. We plug the solar disk and we follow the motion of the same ejecta. And as you can see, there are multiple coronagraphs which is shown here. These are all in Saha satellite, which is also there in Lagrange at one point. Launched in '95, still working. And I was fortunate enough to work on this satellite data, just after my PhD. And then what you see is other spacecrafts are also looking at the same object from another vantage point. So this movie also explains that if you observe the sun or all these motions from one vantage point, you have the information in the plane of the sky. You do not have really information in the 3D mode. So if you want to really see the 3D mode operation, then you have to have multiple satellites on multiple vantage points so that you can reconstruct that image and its motion to get a realistic speed. Otherwise, what will happen is the speed what you calculate is in the plane of the sky. And today what I am going to talk about is these, arrival time of this ejecta to the Earth is a very, very important exercise to protect our assets. So I will again show you example. This is Parker Solar Probe. This is again another satellite which is going much closer to the sun. And it is going so close to the sun, it cannot really directly look at the sun even. It has a coronagraph imager which is looking away from the sun, and you see I don't think it is a very nice environment to be. So it is really very violent. Of course, our satellites are not going that close anywhere, but when this ejecta, so violent ejecta is traveling into the interplanetary space, we do have to now, save our assets in the space as well. You also see the Milky Way for this nice little images from the part of solar probe. So this is the state of the art what NASA is doing now. Of course, this is again another example of stereo spacecraft from NASA. So there are two identical spacecraft, stereo A and stereo B, and they are looking from two vantage points to reconstruct this ejecta's motions. And as you can see here, that this is close to the sun, and the ejecta comes, then it travels all the way to the solar corona, then we call it heliosphere, and this is the near Earth environment. And these movies are made from not one single instrument. The other point is these are made from a number of different instruments, coronagraph of different field of view, heliosphere imager with different field of view, and then you combine the information. So I'm trying to highlight that how important it is to really be part of this, international scenario to get a comprehensive view. Of course, we have our magnetic field, and that protects us. But of course, what I will show you today is that the satellites are outside this magnetic shield, and they are continuously exposed to this kind of stuff. And this is again just animation to show that if I could have been just a simple magnetic dipole, and if there would not have been sun one side, the magnetic field lines would have looked like this. But since you have a continuous, particle bombardment from the sun, also in the form of a solar wind, which I did not talk about, the sun also is a magnetic star, so it is a continuous, expulsion of material in the form of particles, which is called the stellar wind or solar wind in this particular case. So when an ejecta comes, essentially, you also need to understand the solar wind first, and then the ejecta is thrown into the solar wind. So what will be the effect, final effect of this? I often give you this example that we have to put this, throw stones in the river. The river is flowing and we just throw the stone. Depending on at what speed you throw the stone and what is the speed of the river on a motion, it will dictate, how far your stone will go. It can die out within this, or it can go travel further. So it's like this. So the solar wind is there, is the background, and then you have these coronal mass ejections which is coming, and then it will be, deciding at what time it will reach our near Earth environment. But then again, what is the magnetic properties of these ejecta? Because these are not neutral particles, they are magnetically charged particles. So this cloud has a magnetic field, directions and all that. Depending on the magnetic field properties of these big magnetic clouds and Earth's magnetic field direction, we will have, whether we will have a very severe interaction or not, those kinds of things are also involved. So here, this is why you see the beautiful aurora, of course. The charged particles, they cannot penetrate the magnetic field lines, they guide along the magnetic field lines, and they try to get through the polar, leaky region. And that's the reason of seeing the beautiful auroras. There are, of course, chemical effects in the chemistry in the Earth's atmosphere. But then, you have also very severe impacts. These are called geomagnetic storms. So as I said, near Earth magnetic field, and majority of the people here in the radio physics department has been primarily focusing on these kind of effects and effects in the ionosphere and so on. So it, of course, it disrupts our radio communication. It can disrupt our power systems, our GPS systems, impact the satellites. It can delay our WhatsApp delivery, or few hours of TV shows disruption. So essentially, it is space weather which has become a very, very important area in modern day. And you talk about the lower Earth atmosphere, the ionosphere heavily getting impacted. There is a lot of atmospheric drag which changes the satellite trajectory. We need to understand. Tomorrow we are launching, we are also watching actually what is happening in the sun. Because if there is a big solar storm, it will change the solar wind and the interplanetary magnetic field structure. So whatever is the trajectory calculated for the satellite will be diverted. In fact, the SpaceX launched 40 satellites 1.5 years back. They lost all the satellites. It's $1 billion loss. So I think in the modern day, it is very, very important now to understand this space weather. Very similar to Earth's weather. Of course, everyday life becomes more affected by our climatic weather changes. But here we are talking about 50,000 crore, assets of ISRO in space and protecting them. So with all that, we are going to Lagrange 1 point, and I will be talking about this mission. This is a multi-institutional mission. Primarily, the payloads have been, designed and developed in certain academic institutions, namely the Indian Institute of Astrophysics, Inter-University Center for Astronomy and Astrophysics. Ajit was the director at that point of time when SUIT instrument was, given to IUCAA. Of course, there are many ISRO centers which are directly involved. So without ISRO's active role in the collaborations, none of these instruments would have been possible to be delivered in time. Of course, for such a mission, it takes almost more than one solar cycle. So I've plotted the solar cycle in the background. We started talking about it for a low Earth orbit, way back in 2006. This was an ASI mission document, which was again, since we are talking about, G. Srinivasan from RRI, he called some of us for a presentation in RRI, and we were talking about a coronagraph, imaging coronagraph. At that time, it was only an imaging coronagraph, which was approved by ISRO in 2009. But then suddenly, 2013, Professor U.R. Rao, the chairman of the ARPOS, Ajit was also part of the ARPOS at that point of time, he just came up with this brilliant idea. Why are we doing this small thing, small baby steps at one time? Why can't we do big mission? Like, why don't we go to Lagrange 1? I mean, actually, some of us were even younger at that time, and we couldn't even believe what we are hearing from him. Because Lagrange 1, it's only ESA and NASA has so far been able to successfully reach. So India can attempt to go to Lagrange 1 point was itself a big, story for us. Of course, announcement of opportunity was given. 7 payloads were selected after a lot of review. Of course, we took quite a bit of time. There was this solar minima period and the COVID coinciding. But we are lucky. Finally, the payloads are all delivered early this year, and we are launching tomorrow. So we are in the African phase. And I think it's a great time for the Indian space program, Indian astronomy. We have seen the success of Chandrayaan. It's actually internationally I'm getting so much of calls and so much of appreciation for what we are doing. So that's the first few days of work. This is liftoff at 11:47 to be precise, and we are going to be on this PSLV, and then it will be insertion. So the orbit looks something like this. It's very similar to the early part, is very similar to Chandrayaan. These are called heart-centered orbit transfer, and then slingshot, and we are thrown into the cruise phase. So we will exit the SOI. It will take almost 4 months to reach to L1 insertion point. So please be aware, this is a crucial, heartbreaking time for us. This L1 insertion is very, very crucial. It's very similar to the Mangalyaan, capture. The orbiter, there was always tension that we have to get into the gravity of Mangalyaan, so that means we have to have the perfect entry with the perfect speed and so on. So that's a very, very crucial maneuver, and others have not been successful. China tried it in the past, they were not successful. So that's a Lagrangian mission so far. Wind, ACE and SOHO, these 3 are successful, L1 missions. Of course, L2 is fantastic, and you all know about the recent entry there with the L2. So these are special vantage points. If somebody has questions why they are special and all that, but essentially once we reach L1, for any two-body system, essentially if you want to move around that orbit, you need a centripetal force. So the centripetal force is essentially given by the force balance between Sun and the Earth. So once you reach there, you can actually be there for a very long period of time. So although it is a 5-year nominal mission, we expect to last there for more than one solar cycle. We are also taking some help from ESA. This has not been always acknowledged, but ESA is providing us ground support, and ESA has a huge network, but for the initial period only, for the launch and so on. And as you can see here, this orbit needs a little bit of maneuver also around L1. But that maneuver is once in 2 months only. So the fuel which is necessary is once in 2 months, just to ensure that you are in a big hello orbit around Lagrange L1. So the initial period we will be taking ESA's help, because they have a network of ground stations which we do not have. So this is something which we also found out, and so that's the journey to the L1, and that's our Aditya is moving towards that. Hopefully we will be there very soon, and we will be orbiting this. So these are nice little animations done by my students. So the students are very smart these days, because always I say, because I have to give more public lectures and so on. So please give me some material, and this is what I got yesterday night. There are other Lagrangian points also, namely the L5, which is very good for solar observation particularly, because that can actually look at the sun from the side. So what we see in the front side from sun and line, we can see it almost 5 days or 6 days in advance. So this is a big thing for space weather as well, because we don't know what is coming into the sun-earth direction. So if we have early things from the side, and incidentally again Professor Yuvarao, unfortunately he is no more, but he already initiated a possible mission to L5. So we really are thinking big from India. Major objectives, see I can spend probably 1 hour for each of these items, but unfortunately I don't have. So the coronal heating and solar wind acceleration, as probably some of you are very well aware, that the corona is much hotter than the photosphere. It's millions of degree Kelvin. It has been always a mystery. How the corona is maintained at that high temperature all the time. We do have a lot of understanding, but still we do not have the full understanding about how this corona is maintained at. And as I indicated, the sun has its continuous wind, but then how the wind gets accelerated, it only initiates with few tens of kilometers very close to the sun. But we know that at a larger distance, it is several hundred kilometers. Again, there is a latitudinal difference. When you look at the equatorial direction, it is only 200, 300 kilometers. But if you look at the polar region, it is 700 kilometers. So how the wind is accelerated to these different values and all that, we still do not have an understanding. As I also showed you that the different layers of the atmosphere is really coupled, they are not in isolation. Of course, in Earth also it's the same thing. They talk to each other. To understand these, you need multiple wavelengths. So this is a unique opportunity, because Aditya has a suite of multi-wavelengths from optical, near UV, infrared, X-ray. So that allows us to probe all these different temperatures, and then talk about the solar wind distribution, as I indicated that it is very much asymmetric. You have slow solar wind, we call it in the equatorial region, and the fast wind in the polar region, and so on. And then why these ejectors or the coronal matter ejections do happen? What is the initiation process? There are n number of there is no unique sunspot active region. Every other active regions are different. But there has to be certain physics which should be able to explain the initiation or instability of these magnetic structures. So to understand that, we need to look very close to the sun, and some of our instruments have this, and of course the near Earth space weather, because before these ejectors arrive Earth, it has to pass through Lagrange at one point. So at the Lagrange at one point, we have in situ instrument which will allow us to really measure the particle, their charges, their masses, their magnetic field properties. So this is called the in situ instrument at Lagrange point, will allow us to really predict what we are going to do. Too many calls from ISRO is coming, including the director, but I have to take all later on. So there are certain uniqueness. First time specially resolved solar disk in the near UV band. The CME dynamics very close to the solar disk. CME which is observed consistently with multiple payloads and so on. We have also for the first time tried to build some onboard intelligence. Because one disadvantage of going very far is the telemetry. Because we are not going to see the satellite all the time. If the satellite is in a geostationary orbit, then we can download the data at any time because we have the direct visibility. But when you go farther away, your visibility is your total amount of data which you can download is very limited. So you have to select what is important, what is not important. So that means you have to have intelligence on your observation. You take several images, but you throw away a lot of images, only store the images which are important. So such kind of onboard intelligence has been implemented in a couple of payloads now. And then, different of anisotropy and all that is there. So that's the payload, distribution. We have the two particle detectors. So the biggest payload is the coronagraph, which is built at IAA, 170 kg elephant, and is sitting in the top deck. And next is the solar ultraviolet imaging telescope, which is built in Ayuka. It's a 30 kg near UV full disk imager. And the other guys are much, smaller, we can say babies. This is the full poster I have. I will actually have another visit in a couple of days' time. So if somebody is interested, please ask them to come to VITM. So essentially, as I said, the major scientific objective, uniqueness, and all that. So there are a number of resource material available in Aditya, support cell website and also ISRO website. First time we are. That's why ISRO, public outreach director is also calling me for more updates before the launch. So these are the details of the different payloads, and as you can see, this amount of information is now we are trying to make available to the public. As I indicated, the coronagraph and the suit instrument is the top deck. These are the other particle detectors. Their last January schedule. What is important is to again realize that the space is filled with so many satellites from different space agencies. We are not alone. And all these years we have been using actually these data. But what we have tried to build here in India is with some uniqueness which complements this, which others do not have. So you have to identify what is the gap in different telescopes or different missions, and then try to design, the one which you can, complement this. So there are about 20 operating missions with 27 spacecraft. 13 missions are the formulation and implementation phase, and Aditya we are going here near the Soho and ACE and Wind, that Lagrangian 1 point. We are out of Earth's magnetic field, so that again is a very special vantage point. Of course, there are plenty of satellites within the magnetosphere as well. All these, it's only possible when we have more users. So again, this is an effort which we have initiated this time around before the launch. This is called Aditya L1 Support Cell at Aryabhatta Research Institute, and I am heading that effort. Similar to AstroSat Support Cell, which is still there in Ayuka. Of course, Ajit led that effort at that point of time. So, and Dipankar Banerjee, my namesake. But this is a very, very important exercise because, the people who build the instruments, they understand the nitty-gritties and they are the maximum users. But, these are national missions of, 400 crores worth. So, we should have more users for this. That means you have to train more people, and the people who understand the instruments have to take the responsibility to train, younger guys all across. So we are conducting several workshops. Probably there will be one in Kolkata in December as well. The next one is in IIT Kanpur in the last week of September. We just got the application, 400 applications were there, we have to only select 40. So if you are not selected, please come for the next one. This is a talk which is scheduled on 6th. Hopefully everything goes all right. I will be back in Calcutta on 6th. VITM, we are going to spend the whole day with lots of poster, hands-on. So please convey this message to your friends or colleagues. I'll be happy to explain much more than what I have done today. Thank you for your patient hearing. I come from a beautiful place in the Himalayas, and you can visit Nainital as well. I'll be happy to take you around. And Jai Hind, and that's my chief. questions or we will?
Couple of questions we can take. If there are any.
So, hi, sir. I'm Chatterjee, I'm a faculty member at Distance University. So, the in situ magnetic field measurement that one of the instruments Aditya will do, what is the expectation that the solar wind is carrying the magnetic field, or what kind of expectation?
There are two things. There is already interplanetary magnetic field. So that's the background. And then on the top of that, it's the CMEs which carry the magnetic field from the sun. So the CMEs are like a magnetic cloud, which also has its directional properties. And the directional properties of the CMEs are very crucial to understand the impact when it hits Earth's magnetic field. So the idea is that we will measure the magnetic field. We'll try to measure the magnetic field of the background, interplanetary medium. We must point out, since you asked the question, the satellite is not magnetically clean. So the magnetometer was not originally designed because India doesn't have that technology. But then what we did is there is a long boom, and in the boom there are multiple probes. So the expectation is that from the differential measurement, you could get an estimate what is caused by the satellite itself and what is there from the background what you will. So it's differential amount which we'll be measuring. So more precisely I would say we will have a capability of measuring the magnetic field of the CMEs rather than the interplanetary magnetic field. The interplanetary magnetic field itself is very, very weak, and that variability will get affected by the satellite operation itself. So the CME magnetic field measurement is more crucial. We'll be attempting, of course, interplanetary magnetic field also, but we have, it was not originally designed for that.
Thank you.
I have a very late question. That like in case of Chandrayaan 3, what's the kind of travel time that we are common person?
Yeah. So I just indicated that it will take 4 months to reach Lagrangian 1 point. So initially the Earth phase is there, which is not very long, but then the cruise phase is 4 months. So this is, I think, there will be depending on the orbit numbers and all that. So it will be only few weeks, but then that journey is much longer. First week of January, we were told, is the L1 insertion. And then once we reach L1, one by one the payloads will be opened. First the suit instrument will be opened. It just disappeared. You will have tension.
What is the life?
Yeah. So the nominal life is 5 years, which is guaranteed. But majority of the informations, whatever they are saying is nominal, it is lasting for much longer. And for reference, Soho, which was launched in 1995, is still alive. Soho had 13 instruments. All the instruments do not operate with the same efficiency. Some of the instruments do not work, but the satellite is still alive. So the instrument's life depends on what kind of dosages it is going to get, how sun becomes too active, or how many CAVs are going to bombard on that and all that cosmic ray hits. So, but at least 5 years. So that's the term called nominal.
I think we're still there.
Sir, I have a quick question. That I think in L1 point, the energy wattage is 3 kilowatt per meter square. So there will be a high temperature, and sometimes the CAVs are also too hot. So it is very difficult to maintain electronic components at that temperature. So how can we just adjust?
It appears that you have more knowledge than me in terms of the numbers, but one thing we have to realize is we are only going 1% of the distance. It is not like the Parker Solar Probe, which is going much closer to the sun. 1%, 1.5 million kilometers. From here to sun is 150 million kilometers. So it is not a very hot environment. It is not a very hot environment. Having said that, there are going to be all these bursty events and all that, which carries a lot of energetic particles. So that has much more effect on the electronics than anything else. It's not the temperature. In fact, sometimes inside the telescope, we have to heat it to operate it in the room temperature, because some of the optics is designed for 22 degrees centigrade, which is the room temperature. So heat is not a very big challenge.
What is the uniqueness of this?
So there are n number of uniqueness. As I said that for the first time we are going to look with this, I mean if I take one by one the instrument itself, the coronagraph is going to look very close to the sun from 1.05 to 3 solar radius. I showed you in movies, I ran it too close. You'll see that the solar disk was blocked to a very large distance away. Because as close you go, you have a lot of issues with the scattering and all that because the sun solar disk
That type of geeks available from Saha mission or?
No, Soho's there was a C1 coronagraph. It did not work more than 1 year, unfortunately. And that time it was a solar minima period and all that. So we do not have an inner coronagraph in space up to that distance. Also, we have now 10747. This is an infrared line. We are going to first time attempt to measure or get an estimate about the coronal magnetic field, which has not been done from space. There have been very limited success from the ground. So this is again a dark energy problem of astrophysics, because ultimate thing is all about
That
magnetic
is
field.
coronal
understand?
magnetic field you are saying, that is differential magnetic field. That is already there is solar wind and phase magnetic field.
Yeah.
And now you are calling CSG.
So that is interplanetary magnetic field, what you have in, but essentially that interplanetary magnetic field comes from the sun and those are steady fields. But what I am talking about is we do not have a direct measurement of that field. We have models which gives us an indication that the field could be 2 Gauss, could be 20 Gauss, could be micro Gauss, but there is no direct measurement. There are models only. So for the first time, like Zeeman effect is used for magnetic field measurement in the photosphere of the sunspots, we are going to do spectropolarimetry here to get an estimate about the magnetic field in the corona. So these are new experiments which is going to happen. So there are a number of such unique attempts, I would say. Yeah, I have to give him chance, please.
So, what is the typical length of the orbit?
Yeah, so the orbit is also actually not, it's in the plane of the sky. I am showing it as a single thing, but it is not actually a single one planar thing. It is going to be like a Lissajous figure actually. If you remember Lissajous, yes. If you remember the Lissajous figure, ask ISRO to provide those animations, which they have not released it. Because these are some of the trajectory things are very critical and they don't release it. But it is like that. It's a three-dimensional thing. So it's not that simple.
Thank you.
Very silly question. Your heart is appearing to me as black because no light is reaching me. Over the sun surface, black holes are also black. Is there any difference between your heart and black holes?
Yeah, because this shirt is not emitting anything. It doesn't have the temperature to emit, whereas the solar atmosphere is very hot and you have lots of transitions. So things get ionized and then you have a transition to a higher layer, and from higher layer to lower layer when you get emission. Right? The energy, the excess energy is emitted. So all these are for emission lines. On the other hand, you can have absorption also, because sun also is a black body which is emitting at 6,000 Bohr, right? So you do have a background, light which is itself emitting, and black hole, I think Ritovan will be, of course, black hole cannot emit anything because that's the definition of the black hole, that all energy is absorbed inside. So this is a quick answer probably.
Okay, so
I don't want to explain car matrix here.
so more questions we can take offline. So with these things, I thank from the department on the behalf Professor DIpankar Banerjee for his illuminating talk, and as a token of appreciations, I request Professor Animesh Maitra to hand over a small memento to him.
That book is actually written by one of the authors is Professor B.K. Basu. Along with him, Professor S.C. Dr. Rai is also there. And it tells about the various teachers of our department, illustrious teachers. So thank you, Dr. Banerjee, Dipankar, to many of us for sparing his time.
It's an honor for me to be here, and also I would have loved to listen to the other talk, but